Welcome back. Now, this is my third lecture on IR spectroscopy. Now, in last lecture, we had discussed about the three vibration modes of water. Now, we will discuss CO2 molecule. CO2 molecule is basically linear as it has three atoms, two oxygens, and one carbon. Therefore, it has four fundamental vibrations 3 into 3 minus 5. The symmetrical stretching vibration is inactive in the IR since it produces no change in the dipole moment of the molecule. The bending vibrations are equivalent and are resolved components of bending motion oriented at any angle to the internuclear axis. They have the same frequency and are said to be doubly degenerate. Here in this diagram you can see the symmetrical stretching and asymmetrical stretching of carbon dioxide. There is two types of bending here, the scissoring, and both you can also see that the frequencies are also mentioned with the diagrams, and you can clearly observe that the symmetrical and asymmetrical stretching basically is arrhythmical, and in bending we have observed the type that is called scissoring. Now the various stretching and bending modes of any AX2 group appearing as a portion of the molecule, for example CH2 group in a hydrocarbon molecule, will also be discussed. And here the 3n minus 6 rule does not apply since the CH2 group represents only a portion of molecule. The theoretical number of fundamental vibrations, or you can say absorption frequencies, will seldom be observed because overtones, which are basically the multiples of a given frequency, and combination tones that are sum of two other vibrations, increase the number of bands, whereas other phenomena reduce the number of bands. The following will reduce the theoretical number of bands. We will discuss them one by one. First of all, fundamental frequencies that fall outside of the 400 to 4000 per centimeter region. Then fundamental bands are when fundamental bands are too weak to be observed. Fundamental vibrations are so close that they coalesce. You can say they combine or coalesce. The occurrence of a degenerate band from several absorptions of the same frequency in highly symmetrical molecules. The failure of certain fundamental vibrations to appear in the IR because of the lack of change in molecular dipole. These are the 5 reasons when the number of bands are either they disappear or they are reduced. Now we will discuss the application of Hooke's law. In the application of the law, two atoms and the connecting bond are treated as simple harmonic oscillator. We will suppose that it is a simple harmonic oscillator that is composed of two masses joined by a spring. And here I have written the equation. If it's visible, I will turn the can observe this equation, that's Hooke's law. Here you can see that I have written the Hooke's law, where mu naught is vibrational frequency in per centimeter, c is the velocity of light, f is the force constant of bond, and mx and my are mass in grams of atom x and atom y respectively. The value of f is approximately 5 into 10 raised to the power 5 dynes per centimeter for single bonds, and approximately 2 or 3 times this value for double and triple bonds respectively. The force constant F can be thought of as a measure of bond's stiffness. The force constant can be correlated with such properties as bond order and bond strength, because the frequency is directly related to the square root of the force constant. And we know